Uh, Today we will discuss about the power converters so that are required for the drives applications, right? So you know that the power converter is essential for all drive. So first we'll start with the basics of the power converters. So next we'll discuss about the how high power inverters or the high power converters are required, and so next we discuss about they will not follow this pattern. Next we will discuss about the fault tolerant operation of the converters, and also we'll discuss about the modular multi-level converters for high power applications, especially high power drives aimed for application like the ship propulsion units, like that, right? Also we'll discuss about the reduced switch count multi-level inverters and their PWM methods. So you know that, right? So high performance inverter is essential for all kind of applications. Maybe it may be the motor drive, or it may be a flexible AC transmission system, or the distributed energy means grid integration of power converters. So you need to have a high performance converter, so which is essential. So we will operate this converter in usually two modes of operation. So depending on your application, it may be operate in the voltage control mode or the current control mode. So meaning is that so we will control the means the inverter will operate as a controlled voltage source, or operate as a controlled current source. Right. Next thing is that so we need to control the current and voltage inside the converter. So just because to cope with the variations in the DC input voltage, so that means irrespective of the DC input voltage, so we are supposed to regulate the output voltage on the other side. Right. So regulating the voltage of the converter, and in case of motor drive applications, we need to maintain the V by F constant so that the air gap flux will be constant and it will not allow the motor to drive into saturation. And also in case of applications like the grid integration, so we need to operate the converter as a current control mode, and we will inject some current, so which is proportional to the voltage, or which is proportional to the active and reactive power, so that is being injected into the grid. Okay. So power converters have many applications in broad sense. So one is the adjustable speed drives. So next is the hybrid or the electric vehicles. So in case of electric vehicles, so it may be the powertrain or the battery charger. So next is the flexible AC transmission systems, FACTS devices. So these power converters, so which will directly connect to the transmission lines to improve the power flow in the transmission lines. Right. So next one is the custom power devices. Like these are used for the power quality improvement. So one is the series one, shunt one, and the combined both series and the shunt one, that is D-STATCOM. Next one is the DVR and UPQC. So active power filter. So both D-STATCOM and active power filter. So both are similar. So next is the renewable energy. So for renewable energy integration and extraction, like using MPPT techniques, integration like using inverters or the grid following and grid forming inverters, all these required one power converter of rating from starting from the few watts to the few hundreds of the kilowatts. So next is the HVDC and HVDC plus. So HVDC is the converter based, so which use the GTO as the device. So whereas HVDC plus, so that use the modular multi-level converters. So for this direct connection, or the directly connect to the transmission lines. So next one is the grid connected transformer-less applications. So by using these inverters, so we can directly connect to the main grid. Okay. So battery chargers. So this battery chargers, it may be of wide range of power. So if you consider some mobile battery charger, it may be up to 5 watt to maybe somewhere between 250 watt or 320 watt. And if you consider the electric vehicle, so it may be of 1.8 kilowatt to up to 350 kilowatt or something. And if you observe the propulsion units for a large powertrain, so in that case the power means the battery charger rating is in the order of megawatts, 1 or 2 megawatt range. Right. So home appliances, so all these home appliances like the air conditioners, refrigerators, so nowadays work on these power electronic devices. So conventional power converters, all right, this one. So either, I mean, most of the applications. So we need to satisfy the, or we need to control the V by F ratio, right? And also some other applications like we need to maintain the whenever you are connected to the grid. So you are getting a output voltage which is of varying magnitude and the frequency. So in that case, you need to it means you need to regulate that voltage, and you need to match the frequency with the grid frequency. So in that case, what we will do is that so we will convert this AC to DC and convert back to AC with the required magnitude and the frequency. Right. So those are commonly known as the DC link converters. So one is the direct conversion, so AC to AC conversion. So we normally use cycloconverters early days. So those are based on the thyristor switches. And next we have the matrix converter. So matrix converters use the self-commutated devices, right? So matrix converters having several drawbacks. So one common drawback is the switch means it will frequent short circuit in the output terminals, right? So that's why there is no much means compared to this DC link converters. These matrix converters are less used. So we are moving to the DC link converters. So one is the voltage source and the current source approach. So current source approach, again there are several options are there. One is the PWM based one or the line commutated inverter. So line commutated inverters, so they use the thyristor. So whereas the PWM current source inverter, they use the uh, self-commutated devices. So in case of voltage source inverter, so which is very popular, right? So it will be starting from the two-level inverter to the multi-level inverter, right? So we can increase their voltage rating, and they can drastically increase their power ratings up to the 100 megawatt or even 200 megawatt range also. So these are the commonly used inverter configuration. So one is on voltage source inverter and the current source inverter. So here in case of voltage source inverter, you require a voltage source. So whereas in the current source inverter, you require a current source. So practically current source is not possible. So therefore, so here a large inductor in series with a DC source, we assume that the current is constant. So that is how the current source is realized. In case of voltage source, it may be of a voltage source which is obtained from the AC to DC conversion, or it may be a battery, or it may be a charged capacitor, or it may be super capacitor, likewise, right? So if you compare this one, so early days, so we, especially in the drives applications, we prefer to use the current source inverter, right? So nowadays everything is shifted to the voltage source inverter. So why? Because compared to this, or if you compare voltage source and the current source inverter, in case of current source inverter, if you observe that, so two devices will be conduct at a time, right? So the load current will flow through the switch and as well as the diode. So whereas in voltage source converter, at a time only one device will conduct. So one is through the switch. During the freewheeling time, it is through the diode. So therefore the losses will be reduced. And another thing is that the size of the inductor on the current source inverter is very large, and it will make it bulky. So owing to these all reasons, we will move to the voltage source inverter. Even though current source inverters are well matured, we are shifted to the voltage source inverter. This happened almost 30 years ago. Right. And another reason, or what is the good point in the current source inverter, is short circuit protection. So because the current source inverter, the current is constant, so even though one phase leg is short circuited, like upper and the lower devices are short circuited, so here the current will be equal to the source current, right? So whereas in the voltage source inverter, if you short circuit, that means we are directly short circuiting the DC source, right? The current will be huge, that will be damage the switching devices, right? So that's why, so in almost nowadays, in almost all applications, we move it to the voltage source inverter, whether it is a renewable energy source, motor drive, or like D-STATCOM or anything. So most of the times, so we use this two-level inverter. So why it is known as two-level inverter means the idea is simple. Right. So here if you consider this one, right, if you turn on this switch, right, so if you observe the voltage between this point and this point, right, if you turn on this switch, if we assume this voltage is VDC, if we turn on this upper switch, the voltage is equal to VDC, and if we turn on this bottom switch, in that case the voltage is equal to 0. So that's why it is known as the two-level inverter. And another interesting thing is that, so there is no phase currents here, right? So there is no phase current here, so only we have the line, sorry, there is no phase voltages here, so only we have line voltages. So here these are the line voltages, so we cannot access the phases. So if at all you require the phase voltages, the best way is that, so we need to split this DC link to the off. In this way you can get the phase voltages. And also another way is that the load is having, if you connect some load, something like that, right, this load is having the neutral, so from this you can measure the phase voltages, right. But the point is that in case of two-level inverter, so we are interested in the line voltages, not the phase voltages, right. And the line voltages will vary from the plus VDC, 0, minus VDC, right. But it is known as the two-level inverter. But when you talk about the number of levels, so we usually talk about or we usually say number of levels in the phase voltage, not the line voltage. Understood? So you are familiar with this one. So the question is, if you want to go for the high power applications, like you know that, right, nowadays the motors are, in case of electric vehicle, the motors is ranging from 350 kilowatt or something. If the current, the voltage is just 350 or something, right, the current will be in the order of 1000 amperes, right. The current in the machine or each device is supposed to carry 1000 amperes during the peak time, right. So in that case, so what we have to, the 1000 amperes devices are not readily available, so we need to connect the several switches in parallel, right. So the drawback with the parallel operation is that all the switches are supposed to be turned on at the same time, right. So how do you ensure that the turn off should be same time? How do you ensure that? So you know that, right? The first thing is its threshold voltage. So each device is having one threshold voltage. Let us assume if you consider IGBT or the MOSFET, so each device is having some threshold voltage, or this threshold voltage is something like this, or the knee point voltage, or that is the starting point, right? So it's supposed to pass that voltage, so then only the conduction will stop. So here, if one device is having 4 volts and the other device is having some 2.5 volts, so that means the 2.5 volts device will be turned on early. So that means all the current will be bypassed through that device, and it is not capable to that, and the device leads to the damage. So to ensure that, so what we normally do is that before connecting them in parallel, so we have to make sure that their threshold voltages are equal, right. So the thing is that even though they are following the same manufacturing process, but the point is that the threshold voltages will be differ, right. Same process, manufacturing process, everything is same, but due to the material properties, there will be some deviation in the threshold voltages. So that's why in industry they make sure that the threshold voltage is just 0.5 volts difference, right. So that means, so when they will create the bunches. So one bunch 2.3 volts, like that, somewhere between ranging from 2.5 volts to 3 volts. So they will bunch it. So and they will use that devices for the parallel operation. Understood? Right. And even though the main drawbacks with the two-level inverter is their harmonic content. So harmonic contents, so that is the main drawback. So normally if you are using a motor drive, you are expected that, or the motor drive motors are designed to take the sinusoidal input, right. So any deviation in the sinusoidal inputs, so that results in the torque pulsations or the speed fluctuations, right, or the power fluctuations. So therefore it is expecting a sinusoidal waveform. So therefore our main courtesy is to give a sinusoidal supply. Even though whatever you do inside that motor control, the basic thing, so you are supposed to do is that you need to feed a sinusoidal waveform to the motor. So that is essential, right. So whatever the logics you are doing to minimize the torque pulsations or the speed pulsations, the basic thing is that you are supposed to give a sinusoidal input, right. So for that, this is the output voltage that is obtained from a two-level inverter, so which is nowhere close to a sinusoidal waveform. So therefore, what we can do is that, so we connect some filters, right? So normally LC filters, right? So this kind of LC filters is used, right? So this one L will be this one, where, or sometimes we also use the LCL filters or the LCLC filters. So LC filters, so LCL filters or LCLC filters, we are supposed to use this one to make the waveform more close to a sinusoidal waveform. Right. The point is that, so when you are injecting or when you are adding some filters, so here in case of motor applications, the voltage is not fixed, right? If you are using some, for example, you are operating at low speeds, the voltage magnitude is also low. But the filter design, maybe you are designed for at some rated value or something, right? So in that case, so there will be some deviation in the frequencies, right? So deviation in the frequencies, so that will also impact, right? So therefore, the design of filter is slightly complex, so but we can manage this one. So by connecting some LCL filter, by doing some the harmonic analysis, so we can easily, or some something like some resonance analysis, so we can easily design a filter for this. But the drawback is that, so as and when you are adding a filter, so that also includes the weight, and also it will impact the reliability. So one commonly affecting reliability is the capacitor. So capacitor, it is based on the electrolytic properties. After 1 year or 2 years, right, the chemical properties inside that capacitor, it will be altered. So therefore, the resonant frequency may be deviated, or its actual capacitance may be deviated. So that gives you to the wrong tuning, or the tuning may not be at perfect level. Right. And another thing is that, for example, if you choose, or how much resonant frequency you are supposed to choose is that, so in case you are operating this one at a carrier frequency of FCR, so that is the carrier frequency, so that you are chosen for some sign PWM technique. So in that case, so here this converter, if you are using some LC filter, so this one, so this is supposed to be 10 times less than that, right? For example, you are choosing 10 kilohertz. In that case, the resonant frequency is supposed to be 1 kilohertz. So by doing this, so these harmonics we can suppress by 100 times. So by doing this, so these harmonics we can suppress by 100 times, right? So that is the basic criteria. The point is that, so designing 1 kilohertz, means that if you are increasing the resonant frequency, the size of LC will be reduced. So meaning is that if you are designing LC for 1 kilohertz and 10 kilohertz, in that case 10 kilohertz having less required less value of L and C, right? So that's why you are supposed to increase your switching frequency, right? So that's why you need to increase your carrier frequency, so that you can also reduce your L and C values, right? But the drawback is that if you are increasing the switching frequency, that results into the losses. In case of inverter like DC-DC converters, we not use any resonant converters like zero current switching or the zero voltage switching. So that is not a good idea here, because size of the components or size of passive components will not implement those techniques in the inverters. So therefore, it will lead to the higher switching losses, right? And another thing is that, so how much DC value or unique required? Another point is that, so how much DC link voltage you are required. So let us assume that your motor capacity may be some 400 volts. So let us assume that the motor capacity is 400 volts, so which is the line voltage RMS. So line voltage RMS value, right? So in this case, the point is that, so how to select the DC link voltage, right? So here this is 400 volts. So here, depending on what kind of PWM method you are using, so this one, if you are using a sine PWM technique, so in that case you require, so 400 by 0.612, right? So if you are using a space vector modulation technique, right, so in that case you require 400 by 0.707. Right. So that is the DC link voltage, so that you require. Understood? So those are fixed, right? Okay. So not fixed. So this one is the, sorry, this is V line. So V line by, so V line voltage by this one. So meaning is that if you are giving 1000 volts DC, right? If you are giving 1000 volts DC, you will get 612 volts AC. So you will get 612 volts AC. So that is the point, right? So accordingly you can adjust. So and the point is that, so if you are choosing a DC link voltage, so accordingly these switches are supposed to block the DC voltage. So that means each switch is supposed to rated for that value. So how much value it is 1? So it is V line by 0.612. And if you consider some factor of safety, so normally factor of safety is somewhere between 1.6 to 2 times. So that means each device is supposed to block V line voltage RMS by 0.612 into 1.5 or 1.6. Right. So whatever the value you are getting, right? So manufacturer of, for example, if you are choosing IGBT or silicon, means IGBT or MOSFET, so you need to choose the device, right? So how to choose the device? For example, if this one is, you are getting something like 1100 you are getting, right? So let us assume you are getting 1100 if you do some mathematics, right? And you need to see the, so what are the different options that are available from the different manufacturer. And if you see the what options we have, one is the 600 volts devices are available in the market, 1 kV and 1.2 kV and 1.7 kV and 2 kV devices are available likewise, right? So which device you will select? Your requirement is 1.1 kV, so therefore you will select 1.2 kV device, right? You may select 1.2 kV device. So that is the device you will select. So current rating, so obviously depends on the load rating. So depending on the load rating, so you will select the current rating. If one device is sufficient, so that's fine. And if the current rating is huge, in that case you need to connect multiple devices in parallel. Understood? Right. So now the point is that, so if you are using it for the high power cases, right? So this, as we discussed, if it is a motor is capacity of 100 kilowatt or something, right? This is fine. So let us assume that the motor is 100 kilowatt and the battery capacity maybe 400 volts is the battery capacity, right? And if you do some mathematics, what is the current rating or the DC set current? So 1000 divided by 4, the current is 250, correct? So the current is roughly 250 amperes, all right? So roughly the current is 250 amperes. So that means we need to select a device roughly, so 1.2 kV and 250 ampere device you are supposed to select. Understood? So if such devices are not available, what we do is that, as we discussed, we need to connect one or two or three devices in parallel, right? So that's why there is one important point here is that, especially in the electric vehicles, so there are a battery pack. You know what is the size of battery? Voltage capacity? What is the size of battery? So nowadays all the electric vehicles so come up with the two architectures. So one is the 400 volt architecture and the 800 volt architecture. So 400 volts and 800 volts. So that means the battery size is 400 volts, right? You know that, right? If you have one small batteries will be there. So each battery will be provide certain voltage, and that voltage will connect several batteries in series parallel, so that you will get the required voltage. I think there is a name for that. I think 96S and 82P or something is there. So that means 96 switches or batteries in series and 82 batteries in parallel, and each one is having very small voltage, maybe 3.6 volts or something, right? So that is for the 400 volt battery pack. So if you go for the 800 volt battery pack, so just we will double it. So the reason why all all will go to the 800 volt battery pack is that the only thing is that you know that, right? When you are increasing the voltage, the current will reduce. So if you are reducing the current means the I square R losses will be reduced, right? And also if you are using for the charging also, the charging will, if you are 800 volt charging system, it will increase, or you can increase the power rating, right? So why it is important, let us consider two scenarios. One is the 400 volt architecture and 800 volt architecture. So in this case, let us assume the same case, 800 watt 100 watt capacity motor you consider, which is anyway it's very small one compared to that. So if here this one, if in this case you will get 250 amperes, so whereas this one you will get only 125 amperes, right? So you will get two advantages here, right? You will get two advantages here. The first thing is that no need to go for the parallel operation of devices. So usually 125 amperes is a small number, so you can directly get the device, so that we can require only one device. In other words, whatever the devices that require for 400 operation, so that will be reduced to off. That is the advantage. And another advantage is that the I square R losses, or the losses, will be reduced. The losses are reduced. And another thing is that the cable size is there, right? So cable size is, or the cross sectional area of the inside the conductors, so that can also be reduced, right? So only thing is that if you move for 400 to 800, you need to increase the creepage distance, right? 400, if you are keeping this much gap, maybe for 800 volts, you need to increase the slightly gap, you need to increase, right? You know that creepage and the clearance distances, so that you are supposed to increase. So that is the only thing you are supposed to do, right? So that's why for all the performance cars or the luxury cars, so they are moving to the 800 volts architecture. So another advantage is that the charging speeds, if it is 800 volts, so we can inject more current into that. So that means the chargers, so nowadays we have 350 kilowatt chargers are also available. So by using 350 kilowatt charger, if it is the capacity of 60 kilowatt battery pack, 60 kilowatt hour battery pack, maybe it will charge in 15 to 20 minutes, roughly, right? So charging time can be drastically reduced, right? Understood? So this is what it is discussed. If you are using a inverter for high power application, or for example you are increasing the power rating, so what we are supposed to do is that, so we need to increase the motor rating, right? So that is the best option, right? For example, if you consider the ship propulsion unit, the motor rating may not be 400 or 800 volts, right? It will be in the range of 11 kV or 13.8 kV motor you are supposed to use, right? So let us assume that for some ship propulsion, assume that this was connected to a motor, it is of 11 kV motor you are connected, right? So according to that, so here the DC link voltage is supposed to be 11 kV divided by 0.612. So this is the voltage you are supposed to block by each device, right? So it is roughly very huge. I think you will get somewhere around 18,000 volts. So 18,000 volts blocking devices are not available, right? 18,000 volts blocking devices are not available in the silicon range, right? So here what you will do is that you will connect the 3 more or whatever the rating. For example, you get the 3 kV devices, you need to connect 6 or 7 devices in series, right? So here if you observe, what is the drawback in the series connection? So what is the drawback when you have series connection? The failure, right? So here the biggest drawback with the power electronics is that, so as you are increasing more and more devices, so you are relying, or you are reducing the reliability. Not always, you may reduce the reliability. For example, you are connected 3 devices here. So what is the drawback here is that if one device is faulty, right? So one device is faulty, the burden is supposed to share by the remaining 2 devices, right? So that leads to the damage of remaining 2 devices as well. So therefore, normally what they do is that they will slightly add 1 or 2 devices extra. So they will increase 1 or 2 devices extra. Obviously it is a ship thing, right? So reliability is the biggest challenge for them. So they will not worry about the cost and all those things, they will add whatever they think, right? Whatever it will, maybe if they will add 10% or the 20% extra devices. And we have to make sure that the device is supposed to be. And another thing is that series operation, we have to make sure that when it is faulty, there are two options. One, the device will be short circuited or the device will be open circuit. So what is preferred here? It is supposed to be short circuit, right? If it is open circuit, so the device means it will completely open circuit. So entire device will be open circuited, right? There is no current flow. Understood? So here, when you are manufacturing that, there are, if it is inside that, so there are two techniques are there. So one is the press pack manufacturing, and the bond wire and the press pack. One is the bond wire and press pack. In case of bond wire, if it is exceeding the temperature limit or something, right, the bonds or some metallic bonds will be there, so that will be opened, right? So that leads to the open circuit. So if it is a press pack, inside that there will be some springs are there. If it is faulty, so those springs will be attached together, so that leads to the short circuit. Understood? So we are supposed to choose a press pack devices. If it is a bond wire devices, it will be open circuited. Understood? Clear? So this is how you will increase the reliability of the converter. So the drawback is that, so even though you are doing all this stuff, still it is remain as a two-level inverter, right? It is just the output is equal to the same thing, whatever you are getting the same thing, right? The output is equal to this one only. So the output is same like two-level inverter only, right? So again, if the voltage rating is high, the filter rating is also supposed to match with that. The size of the filter, inductance, and the capacitance also it will be drastically increased. All right? And another thing is that I forgot to discuss. So as we discussed here, so nowadays, early days, we have the problem of the switching so this must you need to know, right? So here, so because of the invention of the wide band gap devices, this entire power electronic circuits are slightly changed, right? So earlier days, if you are using for high power cases, we are supposed to go for the multi-level inverters and all, right? But the drawback is that, so multi-level inverters will increase the cost significantly. So why we are the main reason why we are going for multi-level inverter for the industry point of view is that, so non-availability of the switching devices. All right. And the thing is that if you see, these are the silicon-based devices, and when the manufacturers are like the Infineons, Wolfspeed, or the ST Microelectronics, they keep two things in focus. The first thing is that they will increase the current rating as much as possible, or they will focus on the current rating, and the other thing is that they focus on the voltage rating. So for example, if you consider the first device, the power diode, the current rating is, in the first case, if it is voltage 1, it is around 8400 volts, but the current is just 1200 amperes, right? If you see on the bottom, so that is, so 9600 amperes, which is the current rating, but it can block only 1800 volts, right? So if you see that for the IGBTs, so these are the maximum rating that are available. So one is the 6500 volts, and the current rating is of 750 amperes. All right. So if you are focused the current in mind, so it is around 2400 amperes, but the rating is 1.7 kV. Right. So these are silicon-based devices as of now. Right. So you know that, right? So normally for the inverter applications, we go for the IGBTs compared to the MOSFETs. MOSFETs, the maximum rating, if you see here, the MOSFET, it's not here. Normally MOSFETs, at most you will get up to 1.2 kV. Silicon-based MOSFETs, at most you will get up to 1.2 kV only, right? So that is 1200 amperes when compared to the IGBTs, right? So now what happens is there, so because of these wide band gap devices, so everything is changed. So everything is changed, so because of these wide band gap devices. So wide band gap devices, especially we are using the silicon carbide and the gallium nitride devices. So their material properties are something slightly different from the silicon based devices. So if you focus on this one, right? So this one, this yellow one is the silicon based one. So that is completely inside that, right? Okay. So here, so if you means another thing is that if you want for the device properties what we discuss, so one is the electric field and the thermal conductivity, so melting point, electron velocity, and the energy gap. So which device will affect what kind of performance? So there are three things we are supposed to keep in mind. So one is the higher temperature operation. So higher temperature operation. So second thing is that high voltage operation. Second thing is that high voltage operation. And the third thing is that high frequency operation. Right. So high frequency operation. So if you observe that in case of these silicon carbide and the gallium nitride devices, so that will outperform the silicon based device, right? So in every aspect, so it is outperformed. So that's why these are very much popular. So, and if you observe that, or if you see the trends in the industry or industrial production, so these silicon carbide MOSFETs are available. Silicon carbide MOSFETs are available up to the range of 15 kilovolt. So if we have devices up to 15 kV devices are available. So that is silicon carbide MOSFETs. And similarly we have silicon carbide IGBTs are there. So even that is 25 kV and channel devices are also available. Right. So that means you can no need to go for connecting several devices in series parallel. Right. One device is sufficient. Right. So that's why the industry is struggling either they have to select the means either they are supposed to choose the multi-level inverter or the two-level inverters. Okay, all right. So that is the point. And another thing is that this gallium nitride devices or this GaN-FET devices. So these are used for the high frequency applications, but at the low voltages. So low voltage, high frequency applications, they are used in the less than 1 kV applications. We have a lot of applications like battery chargers for the mobiles. So we have mobile chargers. LEDs we have only 5-watt chargers are there. So now we have 250-watt chargers are there. So that will typically charge your mobile. So within less than 5 minutes, means somewhere between 5 to 10 minutes, right? So that much power density. So now that have, and also they are using the GaN-based devices, GaN-FET devices, and the devices are extremely fast. So their devices are operating in the range of 2 megahertz. So that means in 1 second, the switch inside there that is on and off by 2 million times. So you can imagine the speed. So if the speed is high, in that case the magnetic circuit will be reduced. The magnetic circuit will be reduced, meaning is that, so that will make the circuit compact. Right? That means the power density is increased. All right. So that's why these things you need to know. So this is what it is summarized as silicon carbide devices are used for the high power applications like the electric vehicle drivetrain or the renewable energy integration and all. So whereas this GaN devices are used for the high frequency, low power applications, right, like mobile chargers and all. So this is what we discussed, or it is what we summarized here. So another interesting thing nowadays is that what kind of package we are using, right? So you know that, right? How many, if you observe any MOSFET or something, right? So how many terminals it have? So all are 3 terminals, right? So one is the gate, source, and the gate, source, and the drain. So there are 3 terminals, right? So now we have devices with 4 terminals. So that extra terminal, so which is known as the Kelvin sense pin. Right. So Kelvin sense pin. So why we are using that fourth terminal is as good as a source pin. So that means we have two sources are there. So here the point is that where we connect the firing pulse between gate and the source, right? So between gate and source we connect the firing pulse. So instead of connecting between gate and source, so what we do is that, so we'll connect this between the gate and the Kelvin sense pin. So this pin is especially designed to connect the firing pulse. So why we are connecting this one, and what are the advantages you will get this one, and for that you need to see this slide. Okay. So there are two scenarios here. So one is the 3-pin structure and the 4-pin structure. Right. So if you observe that the 3-pin structure, so here inside, just immediately after down the MOSFET, you see some small inductance is there, right? So which is known as the parasitic inductance. So which is the one, so that plays a crucial role, especially during the turn on and turn off times. So this parasitic inductance, so with the parasitic capacitance of the MOSFETs, so that will form some resonance circuit, so that will provide the ringing effect. If the ringing will be during turn on, the ringing will be something like this. So if you are ringing, so the disadvantage is that sometimes it will exceed its threshold value and it may lead to the failure. So that is one thing. So, and another thing is that the switching will not be appropriate. The switching is not proper, right? We expect a sharp rising and falling edge of the pulses. So that if it is not happening, so that means we are having extra losses. Understood? So here, this one, if you are using this one, right? So this is also included in the gate driver circuit, right? So that means the gate pulses itself are distorted, right? So to avoid that, so inside that we will connect this one. So this is bypassed here. So that means this is not coming directly into the load path. Understood? So whatever the parasitic effect is there, right? So now we are reducing it. So that means we are giving a clean pulse to the MOSFET. We are giving a clean pulse to the MOSFET. And we can expect that we will also get the clean pulse from the output. Understood? Right. So what is the advantage here you will get is that, so this will drastically reduce the switching losses. So this one, this blue one is the 3 level, and this is 3 pin, and this is 4 pin, and whereas this one is the 7-pin structure. So this is 7-pin structure. So there are multiple source pins are there. So we have one pin is for the gate, drain, and multiple source pins they usually there. Right. So this one is normally T0 243 247 3 structure, and this is 247 4, and this is T0 263 7 structure. Right. So in all automobiles, so nowadays they are using so this kind of switches. Right. So this kind of switches, so they are using. So if you observe that, right, the losses in this circuit, so the losses is, for example, here in this case, if the drain current is 30 amperes, the loss is somewhere around 400 or somewhere greater than 400 watt. Right. You can see this one, if you are using this one, the loss is just 150. You can see that the losses are almost reduced by 1/3. Understood? Clear? If the losses are reducing means you can go for higher current operation. So this is the advantages, or this is the breakthrough, so that we obtain by properly designing the switching devices. Right. Okay. So come back to our actual discussion. So what we are observed that, so there is a tremendous change in the switching devices. So that change is shifting the selection of converters, or it is making more and more challenge. Okay. So now the point is that if you are using for high power applications, as we discussed, we are supposed to increase the motor size. If your motor size you are increasing is that, so you also need to increase the converter size and as well as the DC link size. So now we will see what kind of options so that we are available. So one commonly used thing is that for high power applications, one commonly using the multipulse converters. So this is multipulse converters you might have studied when you study the HVDC application. So two converters will connected in the series parallel or series or parallel, so that you will increase the current rating or the voltage rating. So for that you require some phase shifting transformers. So phase shifting transformer provide the shift between the output or shift between the input waveforms to the converter so that the harmonics will be cancelled out. So meaning is that if this converter alone consists of fifth and seventh order harmonics, so if it is rotating in this direction, right, so whereas this consists of the fifth and seventh order harmonics, so where this rotates in the opposite direction, so if from the source point of view, right, so this fifth and seventh order harmonics will be cancelled out. Alright, so that means the minimum order harmonic in case of 12 pulse will be 11 and 13th. Similarly, if it is a 24 pulse converter or something, in that case you need to connect 4 things in or 4 converters in cascade or series, right. So in that case the minimum order harmonic is 23 and 25. And if you go on this one, this is used especially for the HVDC application. For HVDC they prefer the 48 pulse converters. For HVDC they prefer the 48 pulse converter. The only drawback is that, so in case of producing the phase shift, or how much phase shift you are supposed to maintain, here is that, so there is a one formula for that. So you need to maintain 360 degrees by n. So n is the pulse number. So meaning is that for 24 pulse you are supposed to maintain 360 by 24. So it is roughly, how much it is, 15 degrees, right. It's supposed to maintain 15 degrees here. So that means if this converter is operating at 0 angle, so this is 15 degrees and this is 30 degrees or 45 degrees. Or if you want more symmetry, it will be like this. If it is operated at 7.75 plus 7.75 degrees, and this is 22.5 degrees, and this is minus 7.5 degrees, and this is 22.5 degrees, if you require a symmetry. Understood. The drawback is that you require a complex phase shifting transformer. So normally if you are 30 degrees phase shift, so which is provided by zigzag and star delta transformer. If it is other than 30, like 15 degrees or 20 degrees or something, right. So in that case you are supposed to use a zigzag or the polygon special type of transformers. So you need to have some special design that. So the drawback here is that, so when you are including a transformer means you are adding weight, right. You are increasing the weight, and also transformers, these are directly connected to the converters. So converter having some DC offset, if you directly feed a DC offset to the transformer, the transformer magnetic circuit or the magnetic core may be saturated. In other words, the magnetizing current will be increased, so that it will increase the no load losses. Not no load, maybe it will increase the losses or magnetizing losses. Alright. So that's why, so this is not a good approach nowadays. So there are other options, that is using of the multi-level inverters. So this is how the multi-level inverter concept is seen. You might have studied this one. So if you observe that the first one is the so you have one DC source is there, and there are 2 points are there. This is the point A and this point is 0. So one switch is toggling between A and 0. So let us assume that the point, or we are measuring the voltage across VA and 0, right. So if that switch is touching the A point, right, so what is the voltage across these two? So which is this equal to this VDC. And if the switch is touching the 0 point, or this, if it switch is something like this, right, so if this measure voltage between this A and 0, it will be 0. So that means you are getting 2 levels with this one. So this one is VDC voltage, right, and you are also getting the 0 voltage here. Understood. And another thing is that, or if you are extending this logic to the 2 more, or if you are split this DC link, right, so you have 2 points here. So now it is point 1 and 3, 1, 2, 3. All right. So if this A is connected to 1, right, if you measure the voltage across A and 0, so you will get 2 VDC voltage. If this A is connected to 2 point, you will get VDC voltage, and if A is connected to 3 point, you will get 0 voltage. So that means you will get 3 levels starting from 2 VDC, VDC and 0. Understood. If you are continuing extending this one, so like it is 1, 2, 3, something like this, right? If it is touching 1 point, so it will touch all the, or it will cover all the DC sources. You will get the maximum DC voltage, so which is this one, right? So if you are bypassing one thing, so like if you connect it 2 point, so you are bypassing this upper one. So therefore we are connecting this one. So this way you are getting the different voltage levels. So if you observe this one, so this one is nowhere close to a sinusoidal waveform. This is slightly close to a sinusoidal waveform. So whereas this one, so this is as good as a sinusoidal waveform, right? So when the waveform is sinusoidal, the best thing is that you no need to connect any filters. We can directly feed to the motor, right? You can directly feed to the motor, right? And another thing is that in case of two level, as we connected several switches in series and parallel, right? So here we no need to block or no need to use that kind of devices. So here, for example, you are connecting a device here, so we'll connect one device here, right? So that means that particular device is supposed to block this voltage only. So whereas between these two, if you connect a device, so this device is supposed to block VDC only. Even though the converter, the overall voltage is to VDC, but each device is supposed to block VDC only, right? So in case also, in this case, if you let us consider some 4 or 5 devices, if it is 5 VDC, right? But this switch is supposed to block only VDC. So that means no need to go for the high power switching devices. So whatever the existing medium power switching devices, so that are sufficient, right? Understood? So here the first thing is that, so why we are going for the multi-level inverter? The answer is that, so for high power, medium voltage applications, for high power, medium voltage applications. So the thing is that, so we can use the matured medium power semiconductor devices like 1.2 kV or 2.3 kV devices, so that are sufficient. So no need to go for the 15 kV or 6.5 kV devices, which are very costly. And another thing is that if you compare the cost between some, let us assume we have 3.3 kV devices 2, and if you compare with 6.5 kV device, usually the 6.5 kV device will be much more costly, right? No, you know that, right? When we are doing my PhD, at that time the inverter cost is almost 1 lakh. So now the inverter cost is not more than 10, it is just less than 10,000, including all driver circuit and everything, right? So that much reduction is there nowadays. Okay. So as the mass production is starting, the prices will be very much reduced, right? The same way, so if you are using a matured, already existing, so well-proven devices, the cost will be come down. And they will reduce the EMI effect and the filtering requirement, as we discussed. And they draw the input current, so with very low distortion, if you are using for application. And another thing is that, so all these voltage source inverters are bidirectional. So that means these converters, whatever we discussed, right, those are bidirectional. If you give a DC supply, you can get a AC supply. If you give an AC supply, so that will also act as a front-end converter. So that means also perform AC to DC operation, right? So which is known as the active front-end converters. So that is active rectifiers or the active power factor correction converters. So but the thing is that if you are performing AC to DC operation, so the converter is supposed to operate in closed loop, right? So if it is a DC to AC operation, so no need of closed loop. If it is a DC, AC to DC, in that case the converter is supposed to operate in closed loop, right? And another thing is that common mode noise, so not noise, common mode voltage. So the drawback, you might add the common mode voltage, the voltage of all the phase voltages or the pole voltages, so which is known as the common mode voltage. So why common mode voltage will appear means that the inverter voltages are not sinusoidal, right? So you know that, right? If it is sinusoidal and balanced, if you add all the phases, you will get 0, right? So but the inverter voltages itself not sinusoidal, and if you add all the inverter voltages, you will get some voltage. So that means that voltage is common to all the phases, so which is known as the common mode voltage. So the drawback with the common mode voltage is that, if especially when it is a motor, so motor between the stator and the rotor, there is just some parasitic capacitance. So between stator and the rotor or some moving parts and the fixed part, there is just some parasitic capacitance, right? So when you are feeding this, especially these waveforms, like this waveform which contains the means this common mode voltage. So this common mode voltage of high frequency, right? So if you apply a capacitance to a high frequency, how it will be acts like? You know that, right? Is 1 by XC, right? So X is in the denominator side, right? That means the capacitance value will be very small. So that means it will allow more current to flow through the capacitor. Understood? It will allow more current flow through the capacitor. If the current is more, what happens? So that leads to the higher losses, right? If that is, especially there, if there is current flowing between the starter and the motor, or starter and the rotor parts, or some moving parts, what happens is that inside between that, so there will be some bearings will be there, or some materials, so which are used for, or which are used as a lubricant. So that as you are increasing the heating, so that means the lubricant's chemical properties will be altered, and due to that, it will be that life expectancy of that motor will be reduced, right? Understood? So that's why, so we need to avoid, or we need to eliminate the common mode voltage. Eliminating common mode voltage is itself a major topic, especially in the motors. So the good thing is that when you are using a multi-level inverters, if the waveform is most close to a sinusoidal waveform, right? So that means if the waveform is close to a sinusoidal, if we add all the phase voltages, so that means the magnitude also will be reduced. Alright? So that's why we can naturally eliminate or minimize the, we cannot completely eliminate the, without any other additional controller, we cannot completely minimize the common mode voltage, but we can drastically reduce the common mode voltage. Right? And they are operating at the low switching frequencies, so no need to go for the high switching frequencies. So the normal switching frequency is sufficient. In case of two-level inverters, maybe you can go for 10 kHz or 15 kHz to reduce the filter circuits, but here, so no need to go for the high frequency. And they are fault tolerant, right? So inverters are fault tolerant. For example, if in this case, if one is faulty, right, one thing is faulty, for example, this is faulty, so we can bypass this one, so we can bypass this one, and still we can operate this one, right? So we'll discuss, I have some slides are there, we will discuss that how to bypass the cells, or how to achieve the fault tolerance and all. So these inverters are fault tolerant, and the failure, or the less prone to failure, and this cost is relatively low when compared to the other high power inverters, right? The thing is that, so there are several inverter topologies nowadays available, but there three are the basic building blocks for the multi-level inverters. So one is the neutral point clamped capacitor, not neutral point clamped inverter. Another one is the flying capacitor multi-level inverter, and the cascade edge bridge converter. Right. So first we'll discuss about these. All these are basic building things. There are other inverter topologies which are available in the literature nowadays. So nowadays, even every day, you are one or two, or at least 5-6 new topologies coming into the or adding into the literature. So, but the thing is that, so all these things are compared to these benchmark topologies. Right. So this one is familiar, or you might have studied this one. So which is known as the neutral point clamped, or NPC, or which is also known as the diode clamped multi-level inverter. So which is very much familiar in applications like the medium voltage motor drives, and application like the grid integration of converters and all. Right. So the operation is very simple, as we discussed. If you want, this is a three-level inverter. So three-level inverter means you must require two DC sources, and we need to access the midpoint of that DC sources. So you have two DC sources which are available here, and these are four switches which are connected, S1, S2, and S3, S4. And the point is that this S1 and S3 are complementary. S1 and S3 are complementary. That means these two are complementary here, and these two are complementary here. Right. So meaning is that, so when S1 is on, so that is S3 is off. Right. So both, so at a time both will be off, that is allowed, but at a time both will not be, or both should not be on. Understood? The operation is simple, and another thing is that this diode is there, right? So which is known as the clamping diode, and this clamping diode, so we are accessing this neutral point. So that's why it is known as the neutral point clamped. NPC converter. This operation is simple, so let us assume that these two devices are on, so that means this device and this device will be off. If we measure the voltage between this A point and this Z point, right, which is neutral point, so these two switches are on, so that means this A is directly connected here and this one, so that means so between VA and Z you will get the E voltage. Understood? Similarly, if these two switches are on, this bottom two switches are on, so meaning is that these two switches are off. So now this A is directly connect this point, so this negative DC bus, so that means if you measure the voltage between A and Z, you will get negative E voltage. So that means you will get negative E voltage. Understood? So now the point is that, so how to get 0 voltage? So to get a 0 voltage, so we need to turn off this upper switch. So this is turned off and this switch is on here, and this is, if it's turned off, right, this is on and this is off, because 1 and 3 are complementary. Understood? So now if you observe that there are two paths are there, right? So now there is a connection, direct connection between the 0 and A, so that means you have two paths are there. So depending on the current direction, so whether it is from the, let's assume this entire thing is a motor, right? So entire thing is a motor. So depending on the current direction, so we have one diode will be conducted. So let us assume that the current is flowing so in this direction. So that means the current will flow like this through the switch and through the motor terminals. Right? Understood? So this is from the source to the load. Right? So whereas in the other case, if it is flowing in the from the low or during freewheeling time or during regeneration time, so in that case, so it will be flow like through this switch and through this neutral point. Understood? It's clear? So that means there is no choice for us. So depending on the current direction, so either the D1 will conduct, that is upper diode will conduct, or the bottom diode will conduct. Right. So here, so this is from your, if you directly connect this point means, so you are getting a 0 voltage here. So that's why you are getting a 3 levels here. So that is VD, E minus E, E and 0. So that's why it is known as a 3-level inverter. Similarly, if you do the same analysis for VBZ, so VBZ, so which is also equal to E minus E and 0 voltage. So line voltage, if you observe the line voltage or the line to line voltage, so which is VAB, so which is VAN minus VBN, right? So VAN is varying from plus E, minus E and 0. So VBN is also varying from plus E, minus E and 0. So therefore, if you subtracting these two waveforms, so there is chance that you will get the 2E voltage. So when you 2E voltage, if it is E, VA and E, and at the same time this is also minus E, so you will get the 2E voltage, right? So therefore, in the line voltages, you have 2E, E, 0, minus E and minus 2E you can get. So that means you can get the 5 voltage levels in the line. So meaning is that, thing is that if it is M level inverter, so you will get a maximum of 2M minus 1 levels. That is maximum, not compulsory. Right. So it is get a maximum of 2M minus 1 levels in the line voltage. And another thing, as we discussed, when you talk about the number of levels, so which is always the phase voltage levels. Right. So this is how a simple 3-level inverter will work. This is how a simple 2-level will work. And another thing is that, so these two may be the DC sources. It may be some battery packs, or it may be, if it is EV, it is battery packs. If it is some renewable energy applications, we normally connect a PV along with their MPPT circuits. Top one we have one PV along with their MPPT, and the bottom one we have one PV along with their MPPT circuits. If it is a wind generation, or if it is a wind turbine, same thing, you have the another converter for the this one, so which is directly connected to the 3-level inverter, right? So now if you observe that there are certain drawbacks here. So one drawback is the variation in the neutral point voltage. See, we have capacitor here, right? So your two capacitors are here. So this is the neutral point. So here you know that, right? If the capacitor, if a positive current is flowing inside this capacitor, a positive current is flowing inside the capacitor, meaning is that the capacitor is charging. If a negative current is flow, or in other words, if the positive, if the, in this case, the capacitor is discharging, right? So here we need to ensure that these two capacitors is supposed to be balanced, right? So we need to ensure that these two capacitors are supposed to be balanced. Understood? Right. So what happens if you are not balanced? For example, you are supposed to, the combined two capacitors are supposed to maintain some 800 volts. So let us assume this is 400 volts and this is 400 volts. If you are not maintained balance, somehow it is deviating. This is 390 volts and this is 410 volts. Right. How the waveform or how the output waveform will be? So positive half cycle you will get 390 volts and the negative half cycle you will get 410 volts. So that means clearly we have some DC offset in the waveform. So if the DC offset, if you directly feed to your motor, so what happens? Again, the magnetic circuit will be saturated. Understood? So we are supposed to maintain the voltage across the capacitor constant. We are supposed to maintain voltage across capacitor constant. So this is also widely known as neutral point voltage deviation. So this problem, so which is known as the neutral point voltage deviation. So there are several methods are there to solve this one. So commonly used methods using some space vector modulation techniques. So that is one method to solve this one. In case if you observe the space vector modulation techniques, there are 27 switching states are there. I'm not going to discuss that. So there are some small vectors will be there. That small vector will influence the capacitor voltages. So by properly using those vectors, so we can achieve that. So another commonly used method is that the model predictive control. So by using some model predictive control algorithms, we can minimize or you can keep one switching constraint or one constraint for the controller, or if you feed one constraint for that, so we can minimize the deviation in the capacitor voltages. Right. So this one you're supposed to solve. Right. So this one you're supposed to solve this one. So otherwise, there will be large deviation in the capacitor voltages. If the capacitor voltages are deviated, so the entire operation will be disturbed. If you are left open, right, what happens is that at some point of time, so this capacitor, one capacitor may be becomes 0 volts and the other capacitor will be equal to full 800 volts. So that means the capacitors will be, so one capacitor will be go up like this and another capacitor will be go down like this. Understood? So there are several methods are there. So one or several techniques are there. One commonly used technique is that early days, so connecting some auxiliary circuit like this. Right. So we'll connect some auxiliary circuit to this one, so which is known as the two-quadrant chopper here or two-quadrant DC-DC converter here. So we connect some additional circuit to this one. So the objective is to balance the two capacitor voltages. Right. So let us assume that this top capacitor is excess charge. Let us assume this is charged to 450 volts. Right. So obviously, so this is supposed to be 350 volts. Right. So in both capacitors, your objective is to maintain 400 volts. So somehow one capacitor is excess charged. So what we will do is that, so we'll turn on this switch. So if we observe that one capacitor is exceeding the 400 volts limit, we'll turn on this upper switch, right? So as you turn on this upper switch, this is chopper circuit, so it will charge this inductor, right? Some energy will store inside this inductor. So now the point is that, so how long you will turn on? Until this capacitor voltage is reduced to 400 volts. Alright, so until this capacitor voltage is reduced to 400 volts. That means the charge, excess charge inside that capacitor, we are transferred to the inductor. Alright, understood? So yes. We are sensing those two capacitor voltages, right? Not average. We are continuously monitor the capacitor voltages using sensors. Every instant. Every instant we need to measure. We need to sense both capacitor voltages. Right? So now what happens is that whatever the excess energy in the capacitors, so we transfer to the inductor. Right? And now what we will do is that we will turn off the upper switch. So this switch we will turn off, right? And we will turn on the bottom switch, right? So you know that the inductor current will not allow the sudden change in the current direction, right? So now the inductor current will flow like this in the same direction, but through this capacitor, right? Now the capacitor voltage is recovered. So whatever the excess charge in the first capacitor is transferred to the inductor, and again it is transferred back to the other capacitor. Understood? So this way you can balance the capacitor voltages by using some additional circuit, so which is widely used especially for the motor drives or for the grid integration in early days. Understood? So you can connect some auxiliary circuits. From this auxiliary circuit will transfer from the upper to the lower. Same thing we can do it for the bottom to the upper one. If the bottom is excess charge, that particular switch will be turned on, and we will turn off the that switch. So once that capacitors maintain its reference value, and we'll transfer that inductor energy to the upper capacitor. Understood? This is just a simple technique, and the good thing is that as we these two switches are not complementary, right? And there is a certain there are so many cases will be there. In some case, for example, there will be a case, so both capacitor volts 350 and 350 volts, right? So both are undercharged. You're supposed to maintain 400, but both are undercharged, right? So in that case, no need of this circuit. So we need to draw excess power from the DC supply, right? So we need to draw excess power from the DC supply. Understood? If it is application is from AC to DC, in that case we need to draw extra power from the grid. Understood? And these two things are not complementary. Okay. So if you want to extend this for some higher levels like 4 level, 5 level, what you are supposed to do is that, so again you need to connect some additional circuits or some additional devices, and we need to require another DC sources. Right. This is for the 3 level, 4 level case. You require 3 DC links. You require 3 DC links here. If it is a 5 level case, you require 4 DC capacitor, DC voltage sources. And again you have midpoints are there here. So you have X midpoint between 1 and 2, and between 2 and 3, so you have Y point. Right. Similarly here we have X, Y, Z. This is one midpoint, and this is another one, and this is another one. So you need to access this one, as we discussed it through the diodes. We need to access this one. So this one, this is X, this is how it is accessed through this diode, which is connected between these two. So whereas this one, so it is connected between these two. Okay. So now we made, by using this clamping diodes, we can access the X point. Similarly, we can access the Y point. Understood? And another thing is that there is one thing, if you see this one, right, this is slightly different, D1 dash into 2. So here there is an asymmetry, especially in the clamping or this device rating. For example, this D1 device, so which is connected between this point and this point, right? So this D1 device, so which is connected between these two red lines, right? Understood? So if you turn on, or if you are observe this blocking voltage, or how much voltage is supposed to block, so which is supposed to block this E voltage. Indirectly it is connected between across E voltage, right? So that means the device is supposed to rate for E voltage only. So whereas this one, if you observe this device, right, this is connected between these 2 points. Now how much voltage is supposed to block? So this voltage and as well as this voltage, it's supposed to block 2E voltage. So that's why it is written as D dash into 2. So that means two devices, so which are supposed to in series of same rating. If E rating devices, you are supposed to connect two in series. Understood? So this is one of the things, so you need to keep in mind when you are designing a diode clamped inverter. Right? We cannot have, if diode means you are supposed to connect two diodes in series or the double rating diode, or we need to connect a double rating diode. The same thing here also, you can see this one, right? So this is S2 here, S1, it is S1. Yeah, so this D1 here and this is D1 into 3. So that means it's supposed to block this voltage, so whereas this is supposed to block this entire 3 voltages. Right? Understood? So this is, if you observe that this is actually a drawback, right? This is actually a drawback. When you are observing and you are moving from the 3 level to 4 level and 4 level to 5 level, the structure, if you see that, it is not at all modular. The structure is not modular, right? So we cannot straight away change it to 3 to 4, or in future if you want to increase it to 4 to 5 or 5 to 6, right? So this is not feasible. So we need to alter the entire circuit, right? So this diode clamped inverter is not a modular structure. So this is not a modular structure, right? Understood? So that's why in most of the cases, so we will normally use this diode clamp for the levels up to 3 to 5, somewhere between 3 to 5, so that we used. There is a drawback here. When you are increasing the number of levels, we need to connect so many devices, so many diodes in. You need to add so many clamping diodes, and also, for example, also the capacitor voltage also deviates, right? If you have two capacitors are there, that's fine, right? If you have 4 capacitors are there, in that case, you need to maintain all these capacitor voltages in fixed values. So that is even more complex, right? Understood? So that's why we will not move to this one, or these are the drawbacks here. So that's why we normally restrict ourselves to 3 level, 4 level, or at max 5 level, not beyond that. So as we discussed, this diode clamp is so many drawbacks. So one way to overcome the drawback is that, as we discussed, one way is that adding some auxiliary circuit, and this is another way to achieve this one. So if you observe that these clamping diodes are there, right, they are replaced with the switches. They are replaced with the switches. So this is known as the active neutral point clamp. This is known as active neutral point clamped. The point is that when you have switches, you have a freedom to allow the current in both directions. You can freedom to choose, so this path for your current direction or this path. So earlier you had diodes are there, you had no freedom, right? These are uncontrolled devices. You cannot restrict the charging and discharging of the capacitor voltages. So now you can restrict them, right? So depending on your control voltage balancing algorithm, you can actually choose which device you are supposed to turn on in this one, right? But the drawback here is that, so instead of diodes, you are adding some extra devices, like 6 devices you are adding. When you are adding a device, so not only device, you are supposed to add all its driver circuit and its control mechanism also you need to include, right? So that is a costly affair. And another thing is, if you are going for 4 level inverter or something, right? So you need to add even more devices, right? So that's why it is also restricted to the 3 level inverter only, right? So we studied NPC with auxiliary circuit, and now this is active neutral point clamped, right? So now there is another one, so which is nowadays more popular, so which is known as the T-type inverter. Right. So this is the best alternative for the 3 level inverter, so which is commonly used nowadays everywhere, every book or every industry. If it is a high power case or the medium voltage case, they are mostly working on this T-type inverter, right? So the structure is like this, it is similar to the diode clamp, and here these are same points here. all are same points. Just for brevity I am showing it in the different, right. So let us assume this is VDC and this is also VDC, right. And this one, let us assume this one is on, okay, and obviously this is complementary here. And if you again, if you measure the voltage between this A point and this O point, if you measure the voltage across these 2 points, so how much voltage you will get? How much voltage you will get? VDC, right. Similarly, if the bottom one is on, you will get this is minus VDC, alright. And if you want this one, or if you want 0 level, right, so you need to use this switch, right. So you need to rely on this switch to get the 0 voltage. So if you observe that this switch, so this is actually known as the 4-quadrant switch. So this is known as 4-quadrant switch, or other words, it's a bidirectional switch. So which is known as the 4-quadrant or the bidirectional switch. So this kind of switches are commonly used in the matrix converter. So these switches are commonly used in the matrix converter and the AC voltage regulations. So here, why it is known as 4-quadrant converter? For example, this one, how many quadrant of operation it has? How many quadrants it can work? 2 quadrants, right? This switch can block the voltage in one direction. This switch can block the voltage in one direction, but it will allow the current in both direction. If you have a freewheeling diode, so it is a 2-quadrant switch. If it is no freewheeling diode, it is just a 1-quadrant switch. So that means it will allow the current in this through the switch or through the diode. Alright. That's why it is known as a 2-quadrant switch. So whereas here this is the anti-series connection of these switches. So this switch can block the voltage in both directions and also allow the current in both directions. One through the switch and the other diode, and the switch and through the other diode. Right. These two or these two. Right. So which is known as the 4-quadrant switch. Right. And if you observe that, if when you are anti-series, like there are 2 possibilities are there. One is the common collector and the common emitter configuration, or the common drain or the common source configuration in case of MOSFET. So what kind of configuration is that? Common emitter or the common collector? Common emitter configuration, right? So this is common emitter configuration. So why we are using this common emitter? So you know that, right, where the firing pulse is connected between the gate and the emitter, right? So between gate and emitter we will connect the firing pulse, right? So if you are using a common collector configuration, right, so that means common collector means, so the collectors are connected together, right? So that means you need to have a 2 gate driver circuits, right? So with this configuration, 1 gate driver circuit is sufficient, right? With your common emitter configuration, so 1 gate driver circuit is sufficient. So this also can be done in the other alternative way, like you have one switch here in the middle surrounded by some diodes. Surrounded by some diodes. So this also allows, this also operate as a 4-quadrant switch. Right. Understood? Okay. So this one is commonly used topologies. So this one is widely used in topology, especially for the renewable energy source, motor drives, and for the battery chargers, especially battery chargers of 350 kV kilowatt rating. So they are using this kind of converters, and directly modules are available. So this entire thing is in one module, right? This entire thing is in one module. So modules are something like this. Right. So this one is known as the discrete device, right? This is a discrete device, and these are known as the modules, right? So this one is, if you see this one, right, this is one phase leg, and whereas this one is the entire 2-level inverter. If you see this one, So these are firing pulses for the 6 firing pulse provisions. Alright. So this is A phase, B phase, C phase, and this one is the DC link. Right. So this is known as the module. So normally all the things are available in three forms. One is the bare die. So bare die means there is no casing. So here this plastic one is there, right? So that is known as casing. So there is no casing, so which is known as the bare die. Or discrete device. So this is discrete device. So this is discrete devices. So whereas modules means, so all these things are known as the modules, right? So he have directly you can purchase T-type phase module, one phase like module, or entire T-type modules. So nowadays available in the market. So you can imagine, right? If it is available in the market means, so most of the industries are using that. It's simple things, right? Alright. So this is commonly used and the best alternative for the diode clamp and the active neutral point clamp, right? So why it is alternative? So you can see that the number of switches are less, and the gate driver requirement is also less, and it will also reduce the conduction periods. So earlier two devices are there on the top, two on the bottom, so now you have only one device. And the thing is that, so this device, how much voltage is supposed to block? How much voltage is supposed to block? If both are same, how much voltage is supposed to block? 2 VDC, right? So this device is supposed to block 2 VDC. So this device is also supposed to block 2 VDC. How to calculate the blocking voltages? That is simple thing. So if you observe that you need to see the circuit. So this one, right? All these things are interconnected, right? Blocking voltage, one of the important thing, especially for the inverters. So we need to properly choose that one. Okay, so if you see that, for example, if you want to calculate the blocking voltage for this device, if this device is conducting and this device is off, right? If this device is conducting means this point is connected here, right? And this device is off means this point is connected here. So how much voltage this is supposed to block? 2 VDC, that's all. Alright. And if it is small circuit, this is fine. If it is a bigger circuit, you need to see all the possibilities, right? Some scenarios you will get VDC, some scenarios you will get 2 VDC, some cases you will get 3 VDC, whatever the maximum thing you are getting, so that's supposed to be maintained, right? That's supposed to be selected. Blocking voltage is max, you know that peak inverse voltage, right? Peak inverse voltage and blocking voltage both are same. And another thing is that, so this device, how much voltage is supposed to block? These two devices together supposed to block VDC. So that means, so each device may be blocked for VDC by 2. Alright, understood? So that's why, so this is slightly, means a better, not slightly, so it is a better alternative for the diode clamp. So next one, so which is commonly used nowadays in the electric vehicle drivetrain, so which is cascade H-bridge inverter, right? So this is especially used for the high power motors, so maybe exceeding 1 megawatt, 2 megawatt electric drives, so which is exceeding very high, 1 or 2 megawatt range. So this kind of converters are preferred. So no, combinedly it will block, right? These two switches will conduct together, right? This is series connection. Hmm. We will give a common pulse right here. Same, same. Right. So we'll quickly complete this one. So this one is cascade H bridge inverter. So if you observe that, let us assume your motor is connected here, right? And this is the neutral point here, and two H bridges are connected here. Let us assume that these are the H bridges, so which are connected in the cascade manner, right? You know H bridge operation, right? So this is an H bridge. So how many voltages you will get from this? How many voltages you will get from this? So E voltage 0 minus E. How to get E voltage? If you turn on these two switches, you will get E voltage, right? If you turn on these two switches, you will get minus E. How to get 0? How to get 0 voltage? Top two switches, right? Upper two switches or the bottom two switches, if you connect, right? So you will get 0 voltage, right? So this way you will get the three levels. Similarly, you will get E voltage 0 and minus E. E0 and minus E you will get, right? So if you observe if combinedly, if you are measure, that means this VH1, this is VH1 and this is VH2. Understood? What is VAN? This one. So what is VAN? So which is VH1 plus VH2. Agree? Correct? So if you observe that, for example, if you maintain E voltage here, at the same time this is also E. So what is VAN? You will get 2E, right? Similarly, you can, if you maintain this one as 0, anyone if you make it 0E or E0, so which is E voltage, you can get 0 voltage. How to get 0 voltage? Lot of options are there, right? So 0 voltage, this is 0, 0. That is one option. Again in 0, you can turn on these two switches, get 0, or turn on these two switches, get 0. Or another option is that you can minus E here, plus E here. You'll get, right? And another option is that you can have plus E here and minus E here. Lot of options are there, right? So here we need to know one thing. So this is known as to getting one switching for one level. If you have multiple switch paths are there, so which is known as the switching redundancy, right? So that means for one voltage level you have multiple paths are there, so which is known as the switching redundancy or redundant switch states, right? So why these redundant switch states are used? So these redundant switch states are used for the minimizing the losses, right? So this is minimizing the losses. How to minimize the loss? For example, you know that one device is already on, right? And if you want to use, you want to move for the another voltage level, right? If the device is already on, so that means you can make use that one. You can identify or you can choose a path such that the device is also included. In that case, no need to on the device again, right? So this way you can reduce the switching losses. And another thing is that, as we discussed, we need to balance these capacitor voltages. These DC source voltages are there, right? So all these things are supposed to deliver equal amount of power, right? We are not discussing it, right? But the point is that all are supposed to deliver equal amount of power, right? One should not give excess power and other should not give. If it is all our batteries are connected, right? So we can expect that all are supposed to maintain the state of charging at same level, all right? So these switching states or these redundant switching states can reduce the or used to reduce the switching losses. And another thing is that so they are used to balance the power balancing of these individual capacitor voltages or DC sources, whatever it is, right? Okay. So that means in this way you can get E voltage minus E and minus 2E voltage. So you can get the 5 levels in the phase voltage, right? So the thing is that, so this is scalable. So this structure is highly modular and scalable. How to increase it to 7 level? So just one more H bridge, right? Add one more H bridge, you can increase it to 7 level. That's all, right? Understood? So whereas in diode clamped, that is not possible. It is highly difficult. So one thing is that scalability is most important thing, especially in the renewable energy systems. So renewable energy system, for example, you have some large PV farm is there, right? In future, if you want to extend that, you need to rely on, instead of using another converter setup and all, right? So whatever the existing facility is there, so you can possible, there is a, if it is a possibility is there, you can use that existing thing, right? So this way, for example, if one PV is connected to here, so each DC source you are connecting one PV. In future, if you want to extend that, so if you have 3 more PVs are there, so you can go for 7 levels. So only thing is that a small connections and small changes in the control circuit. That's all. Understood? Clear? So this is known as the cascade H-bridge inverters, right? So here we require isolated DC source. That means this source and this source should not interact each other directly. So you need to have a isolated DC source. So depending on application, if it is application like a STATCOM, so we have a capacitors in case of STATCOM. If it is an energy storage device or energy storage system, so all are equipped with the energy storages like batteries, right? If it is a motor drive, so what else, what you require? If it is electric vehicle, so you need to have a batteries, right? So normally 2 level you require only one battery pack, and here what is advantage here is that, right. So let us assume that this one is a will break. You'll take a break. Okay, we'll take a break for 10 minutes.